This is Katie Bowman's AP problem number 9. So let's start by reading the question. The graph below shows the result of the titration of a 25 milliliter sample of a 0.1 molar solution of a weak acid, HA, with a strong base, 0.1 molar of NaOH. And then it gives us a graph with pH scale on the y-axis, millimeters of the added NaOH. So that means that the weak acid is inside the beaker and we're using a burette to titrate it. And then it gives us this black line graph right here, and I've added my own stuff, which I will explain later. So let's start with part A. Describe two features of the graph above that identify HA as a weak acid. So I've rewritten it on another paper so it's easier to see. Number one is that if you look at the graph, which I'll show again, the pH starts at 3, so it's not a super strong acid where one like HCl would start at around 1. It's starting at 3, so it's not as strong as it could be. And another reason is the equivalence point is above 7. So the equivalence point is all the way up here, and 7 is the line right here. So if the equivalence point was at 7, that would mean that the strength, that would mean both the base and the acid were really strong because they were like pushing at each other and canceling each other out in a sense. But since it's above 7, that means that the base is stronger than the acid, so it's a more basic solution at equivalence point. Alright, so let's look at part B. Part B asks, describe one method by which the value of the acid dissociation constant for HA can be determined using the graph above. So one way to do it is to look at the halfway point, not the equivalence point, which I initially wrote, which is wrong. That's not the same. So you look at the halfway point where pH equals pKa. And so pH, to find the concentration of H plus, is negative log of the concentration of H plus, so you can like have a pH here and find that, or you can find the pH with this. So you can do the pKa at that point, since they're the same, you can do the pKa equals the negative log of the concentration of Ka, and so at where the halfway point is, so it ends at 25 milliliters, so you know at around 12.5-ish, that's the halfway point, or it doesn't end, it reaches equivalence point. And so you see it's at pH of 5, so your pH equals your pKa, so you're going to put 5 here, equals the negative log of Ka, so you're going to move the negative over, and then you're going to move the log over, so you're going to do the inverse log, so it's going to be 10 to the negative 5 Ka, and then you'll just solve for that, and that's how you get it, that's how you get your answer. Okay, so part C asks, on the graph above, sketch the titration curve that would result if 25 milliliters of a 0.1 molar HCl were used instead of 0.1 molar HA. And so this is the curve that I drew. Because HCl is a strong acid, it's going to reach equivalence point at 7 because it's going to be neutralized. And they're both 25 milliliters. The NaOH and the HCl use 25 milliliters of both, so it's going to reach it at 25, and it's going to start at 1, and it's not going to bump up so fast like this one because there's not as much base pushing it, or it's not a weak acid where it's getting overpowered by the base, so it's going to stay more flat and stay on the pH of 1, and then it'll swoosh up and hit equivalence point, and then come up and balance out at 13. Yeah, so it would neutralize at 7. So part D says a 25 milliliter sample of 0.1 molar HA is titrated with 0.2 molar NaOH. So one asks what the volume of base must be added to reach the equivalence point. So I said M1V1 equals M2V2. So this is my NaOH, or I mean, I'm sorry. No, this is my weak acid, and this is my this is my NaOH. So you multiply these two together, and then you want to get V2 by itself, so you divide 0.2 over, and it gives you 0.0125 liters. And then part 2 asks, the pH of the equivalence point for this titration is slightly higher than the pH at the equivalence point in the titration using 0.1 molar NaOH. Explain. So I said there's more hydroxide, which makes the pH go up. So you're using 0.2 molar, so the concentration is higher than it was in the initial question, which is 0.1. So there's even more base overpowering the weak acid. So its pH is going to reach the equivalence point even higher because the base is so much stronger than the acid, and there's even more of a concentration of it, so it's even more than initially was. Yeah, so that's it. Thanks.